All right. Well, thanks everybody. Oh, and did we get the live stream set up? Perfect. All right. Excellent. Well, again, thanks very much for coming out on a Friday night. We really appreciate it. Um, this is a kind of a special event. For those of you who usually attend our first Friday astronomy events, this is a little bit unique. Um, my name is Brian Jackson. I'm a professor here in the physics department. I teach astronomy and physics. Usually on the first Friday of the month, we are hosting the first Friday astronomy event. For those of you who have not attended that before, that is an astronomy lecture that takes place on the first Friday of the month, 7:30 p.m. Usually we're on the other side of campus. But tonight we have special uh, partnership with the Stellar Collective. We've been running, in fact, if you haven't been here all day, we've been running a citizen science workshop all day. It's been really great, a lot of really great talks. I probably just caught the last time. And so if you are here in Boise, we would love to have you come join us at our first Friday astronomy lectures every month. Next month, we'll have Dr. Joseph Vitale, who's an expert on Saturn's rings and the Cassini mission, about that. And then we're going to have someone coming down from the University of Idaho who's going to tell us about supernova. So again, that's the first Friday of every month, 7:30 p.m. If you can't join us here in person, we also have a live stream on YouTube. I think this is being live streamed right now, in fact. So if you Google Astro Broncos, you should find our YouTube live stream. So if you can't join us in person, please join us for that. First Friday Astronomy is donor supported. And so if you like hearing about all the cool astronomy that's going on out there here at Boise State and out in the world, consider donating to our First Friday Astronomy program. We keep information about that out in the lobby. So this event, however, has been sponsored in large part by it's been sponsored by our sponsors up here and in partnership with the Stellar Collective. So tonight we're going to have a little bit of a unique experience where we're not going to have just one presenter, we're going to have three presenters. And instead of a presentation, we're going to have a panel discussion where we ask our experts about their experience in citizen science. And so with that, I'd like to introduce our experts. And I'm going to kind of let them tell you their own stories. So I'm really just going to tell you their names and we'll give them a chance to introduce themselves. So our first panelist is Dr. Ariel Grakowski. Right there. Thank you. And the next panelist in the middle there is Dr. Patrick Troitart. And then Dr. Rachel Hukmala. And let's start, Ariel. Would you tell us a little bit about your background and how you got into astronomy?
Sure. Okay, yeah, so hi, everybody. Thank you for introducing me, Brian. Again, I'm Ariel. Right now, I'm a postdoctoral fellow at the SETI Institute, and what I do is observational astronomy of small bodies. And how I got there, I thought I'd talk a little bit about my academic journey. I started in undergrad at UC Davis in California, studying physics. And while I was there, I really liked my astronomy classes. So I got into doing research with professors. And from there, I applied to grad schools, and I ended up going to UCLA, where I studied planetary science. And that's where I really started getting into what I'm doing now. Astronomy, using telescopes of small bodies like comets, asteroids, and small moons of the giant planets. And then now I'm at the SETI Institute doing something very similar. But specifically, I work with citizen science data. So I work with Stellar, and I run their comet program. And so unlike how my research was in grad school, I'm getting a lot of data every single night. Users upload their data, they take images of comets that I asked them to take, and they upload their data every single night. Whereas in grad school, I would apply for telescope time, and I would get some pretty cool telescope time. Like I got to use the Kent telescope in Hawaii, and that was really special. But I would get maybe 1-2 nights a year, and sometimes it was cloudy, so sometimes I just got no new data, and that was tough. But now I get new data all the time thanks to working with the Citizen Science Network of Unistellar. So yeah, that's the gist.
Patrick, would you like to tell us a little bit about yourself?
Yeah, so I've always just loved science ever since I was a kid. And so like when I was a little kid, my parents would get Discover magazine, which is a really easy magazine to like read about general kind of science stuff, so like dinosaurs and space and ants and things like that. I just loved everything. And then it wasn't until high school when we started taking like specific science classes like biology, chemistry, and so on. I took biology and I realized that was not for me because it just seemed like a lot of memorization. And then I took chemistry and I thought, oh, this is really cool because there's some math involved and it seemed to make no sense. And I took high school physics and I was like, oh, this is great because you can use math to kind of make predictions, right? You can launch a particle and then predict where it's going to land and stuff. And then finally, I took an astronomy elective with the same physics teacher, and I realized that astronomy is just physics in space, and I was kind of sold at that point. And so, yeah, so basically I thought, okay, well, I'm going to try to do astronomy or try to do like physics with an astronomy specialization and see how far I can go with that. And I figured if I can't do astronomy, then I'll have a good physics background and I can do something like that. And so far it's worked out. I'm pretty happy about that.
So I'm Rachel. I feel like I've introduced myself to quite a few of you a number of times, but here I am to keep you in the microphone. I started in science. I grew up in Las Vegas, Nevada, which like all accept light pollution there is really bad. So I moved to Flagstaff, Arizona, which is actually a dark sky city. Started undergrad. And I could see the Milky Way from outside. Just walk out of the dorm room, you can see the Milky Way. That's something I'd never seen before, and it made me just kind of sit back and think, like, why doesn't everybody look at this? Why can't we all look at this? Like, what's in there? So I majored in chemistry. I minored in astronomy. I got a PhD. I was a postdoc here. And now I'm a postdoc at Chapman University. So I'm making my way through, but we do science because I love looking at the stars, and I found a way to do that for work. So.
I'm going to open it up with a couple of questions, and then we'll open up to the audience for questions as well. So be thinking caps on questions for our panel members. I want to harken back to some of the things that Jackie was just telling us about. Obviously, so the citizen scientists in the project have these very meaningful experiences. I have to think that we've made some scientists that are involved in projects like this. So could you describe maybe a very meaningful story, an experience you've had with a citizen scientist, and maybe an impression about how they've been impacted by participating in citizen science? Start, Gabrielle.
Yeah. With working with Unistellar, the Unistellar citizen astronomers, we call them, are a really passionate group of people all over the world. And we communicate with them mostly through a Slack platform. And so I remember just getting started at Unistellar, getting introduced into the Slack, getting kind of overwhelmed by the Slack. There was a lot of people asking me a lot of questions, and I was also just learning about Unistellar. So at first it was all very scary for me, overwhelming. But pretty quickly we did a really cool project on the DART impact, and we were able to see the DART impact with our tiny scopes, and we were able to do a lot of really cool measurements. And so as soon as I saw we got the data in that we could see the impact from our scopes, I knew we had to try to write a paper. So then I get into the paper writing process. It's such a grueling process sometimes for scientists. But for the first time ever, I was doing it with citizen astronomers. And so I was sending them drafts. I was telling them, hey, this is kind of crazy, but I think we're going to try to submit this to Nature. It's like a big deal kind of journal. And people would tell me, like, oh my God, you're making my dreams come true. And I was like, okay. Like, I suddenly realized it became very motivated. Because I was scared. I was scared I was overwhelmed. I was scared to submit this to Nature. I was going to reject it for sure. Why are we even trying? But when everybody got so excited from the project we were doing and from just the ability to be involved and to be involved at such an impactful level, that made me so motivated. And we did it. And once we did it, people were celebrating. We were all like, let's all buy cheesecake and eat it together around the world. It was really a sweet moment. But yeah, so it's really them that makes me want to be
Yeah, Patrick, you study things on kind of the opposite end of the spectrum, the largest,
Yeah.
most massive things in the universe. What about your
Yeah.
projects?
Well, so the people that came in late. So I study galaxy morphology, which is the shapes and structures of galaxies. And I ran a project called Spiralgraph, which was basically having people trace out the spiral arms of galaxies so we could measure their curvature. And so we'd show people images of galaxies, and they would just kind of trace out the arms so we could look at it. But these people, they were so into it. It was amazing. I thought people would just get bored with it and never want to really do it. It would take like a year or two. We could get through 6,000 galaxies. But people were so into it, I was surprised. And then there were users who would so we in the kind of metadata of each image we would also list like this is the survey we found it from. Here you can look at the wide field survey and look at the galaxy and look at the stuff around it. And people would just kind of browse around in the survey and they would find all this like this off the radar kind of stuff. I mean, people somebody found an asteroid. Somebody found a tumbling satellite that was defunct. Somebody found a weird kind of asterism of galaxies that I have never seen before. It was just amazing, like all these things that people have found just because they were so curious about not only what the galaxy was, but what the things around it. So they would just start exploring literally an entire sky survey, just looking for stuff. And they found some interesting things. And then also, like, people were so I guess excited to be part of the project. I mean, there was one person who was, would ask me questions like through the forum, and would like help other people out, but like just ask kind of general questions of other people, like how they do the project. And he contacted me and he was like, is there something else I can do to help out? And I asked him if he was interested in social media, and he said yeah. And so he took over the social media for the project too, which was fantastic. And he did a great job too. So, and unfortunately now the project is like shut down for the moment. But yeah, it was the whole experience was way better than I thought it was going to be. And that's, I mean, I'm not like well versed in citizen science. I mean, this project probably only ran for I think maybe a total of a year or two or something like that. And then we were starting to analyze data. So like the other speakers have worked on the citizen science project for much longer, and it's really amazing like how active and how interested people really are in this. It's fantastic. It's great.
Yeah, Rachel.
So most of my experience with citizen astronomers is actually with public school teachers here in Idaho. So I used to run a program called Telescopes for Teachers. You have heard of it. And we were able to supply teachers in the state with unistellar telescopes to use in their classrooms. And so I think that while it was a lot of work and maybe not something I should have chose to do while I was planning a wedding, but I spent a summer driving around Idaho in a Boise State minivan full of telescopes, giving them out to teachers, and I personally got to meet every single person we gave a telescope to, and I got to talk to them. I got to tell them, this is what I like looking at. I can't wait to find out what you like looking at. And so I think that the impact for me was at a time when I wasn't sure where I was going to go with my science. I met a lot of people that were just excited to meet somebody that was excited about science. And that made me kind of just realize the impact that the community of citizen science can have just on a person and how they choose to make their decisions. So that's fine.
So meaningful projects, meaningful experiences, lots of good successes, but doing science is hard. Doing science is hard, and I think doing citizen science is also very hard. So would you tell us a little bit about maybe some of the challenges that you faced and ways that you managed to overcome them? Maybe the challenges your citizen scientists have faced in participating in your projects.
Yeah, so for us, it involves using a telescope, right? So at Unistellar, if you own one of these Unistellar EV scopes, that's how you're able to participate in the project. And so there's a lot of, once you get your scope, there's learning to do, especially if you haven't used the scope before. And you have to go online on the website, find their tutorials, whatever, learn how to observe at all, learn how to make the specific observation for each campaign. they're each different. Like for comets, it's one of the easiest ones. You just pop it out, open it, you click on the comet that they ask you to observe, it will point to it, you observe for 20 minutes. But for other campaigns, there's little quirks. Like if you want to observe an occultation, you can't just go out and observe at any time in the night. You have to observe at a very specific time because the occultation only lasts seconds. So you have to really know how to catch it and know how to set your telescope settings right. So things like that, you have to set these things up correctly. So I think we face a lot of challenges in people not reading instructions all the way through, or maybe bouncing around from one campaign to the next and not changing the settings properly, things like that. And so we just try to make it easier and easier by when we do get a result back that is wonky for one of these reasons, we're usually able to tell. And when they get the report back, we tell them why. They'll ask often, what's wrong with mine? Or why didn't mine go through the automatic pipeline? Say, looks like you were pointing in the wrong direction or whatever. So there's a lot of just user error that comes with using an instrument. But we have this really big communication platform through Slack and our website, which we're constantly making as easy as possible. But yeah, I think communication is the key for the troublesome kids.
Patrick, interesting. That's spiral arms. What are you struggle with?
To be honest, I feel like the people were great. I mean, when we looked at the tracings, I mean, we flipped through. I mean, our initial sample was 6,000 galaxies, and I literally looked at all of them, and I can say that people are inherently good rather than chaotic in most cases. I mean, there was some random mess in some of these images, but in most cases, I mean, like in general, we had 15 different people trace out the spiral arms, and in most cases, everybody did the same thing. Nobody was just drawing junk. I mean, there were cases of that, but not very many. So inherently, I think, at least in my project, in that first project, people did a really good job. So I wouldn't say that there were many problems with that. I think all of the problems we had were on our end. I mean, because we had these plans, and we thought, okay, we just get these tracings, and then we can move forward, and we'll be able to do this thing really quickly. But man, our plans, nothing works as you expect, right? And so like downloading pipeline data, and we changed, one thing here, one thing there. All of a sudden, the entire JSON file is different, and my collaborator Ian had to rewrite a bunch of code to like filter out specific things from specific dates. It ended up being a mess, and so we learned a lot from that. So going forward with our next project, everything's gonna be standardized. We're gonna, so I think most of the problems were on our end, on the back end. We did a lot of planning, and we thought we planned everything correctly, but we actually should have planned a lot better. Yeah, so we learned a lot from that. But going forward now with the next one, we're going to be more ready.
I asked teachers to stay out past midnight. I asked teachers to hang out with me during their summer. So that was my big challenge. They're great. No shade to teachers. They do so much work. But one of the big problems definitely that we faced is that we have not only teachers that want to go home at the end of the day, but we have students that want to go home at the end of the day. So making sure that we're building enough of a community that the students want to come back to school to look through the telescope, that the students are old enough to make it back to school once it's dark, especially right in the fall and spring when the sun doesn't set until like 10. So those were kind of our big challenges, making sure people understood when they could use the telescope and making sure they were excited to use it at that time.
So, why don't we take a couple questions from the audience? We have some mics out there. Yeah, Ariana's got some mics for us. These questions for our panelists. We've got one right over here. Or Ariana, can you see?
With the advances in these telescopes that amateurs use, where do you see the citizen science going? Do you feel has a direction or what?
Yeah, so our projects that we do with these unistellar scopes really rely on what a great tool it is to have a network. So the fact that we have a lot of people all over the world, if something happens in the sky and it's nighttime in Japan, and daytime here, I can't look at it. I'll message the person in Japan and say, "Hey, can you check this out right now?" So having a worldwide network is really good for acting quickly. Having a worldwide network is really good for monitoring things for a long time. We can look at exoplanets, for example, start it on one end of the world and somebody on the other end of the world can finish the transit. So basically, having a bigger network is always better for the things that we do. For our DART project, for example, the time of the DART impact into Dimorphos, it could only be viewed from the ground on Earth in a very small location of Earth. And that location was areas in Africa, areas that we don't have a lot of telescopes, large or small. But we had a few citizen astronomers. And that's why we were able to get it. We had to really encourage them and say, hey, this is going to be a big deal. Can you please look? So the bigger the network we have, the more chances we'll have of success with these impactful observations that only we can get.
So networking, you think probably that power of the network is really kind of a big strength of citizen science.
Yeah, huge strength and a really impactful tool. So yeah, networking, making the network bigger, always better.
I would like to add something about that. I know Unistellar is very big on community, so do you mind going a bit more into detail about how they prioritize that and encourage community engagement? Because they're really great with that. So
Yeah, I think we work really hard to, again, communicate with our citizen astronomers, reach out to them, and when we go to conferences, we ask for people who we know who live in the area to meet with us and talk with us. Yeah, we're just constantly trying to get them involved in the things that we're doing all the time. And I think that that really helps to encourage the community. And on Slack, we'll create groups when we're working on a project, and we'll say things like, "Okay, guys, congratulations, we all did it. Let's all go out and buy a cheesecake, and we'll all take pictures of our cheesecake and send it to each other." Things like that. Just make sure to communicate.
What do you do to people who are lactose intolerant?
It's you have to sacrifice
You
for
gotta
the group.
sacrifice.
Yeah.
I think it's a little personal thing. Let's get the mic for you.
So I guess my question is, I know, and I just got here, so I didn't know you guys were going all day. Sorry about that. But is it required to use a unistellar telescope? I have a Celestron origin smart scope. Is it possible to be involved in this with something like that, or does it?
So for most of the projects we do, it requires that they be complete solar scope. But we have done many projects where we team up with other groups, other energy groups that have their own telescopes. So like we did a common project with the Association for Astronomy in France, and they all had their very own telescope, and we combined our data and ended up with a really cool result. So we do collaborations like that too. But all the instructions we give on our website are for an scope. But yeah, we do collaborate with whatever data we have. And if you do want to learn to take measurements, like comets, for example, there are other places you can submit your data that are really valuable to me and to comet scientists everywhere, like the COBS database or the Minor Planet Center. The data there can be used by us or by anybody, and we often compare our data to the data being submitted to those platforms. So that's really valuable too.
Well, and let's also, there are, as we've heard today, there are citizen science projects that don't necessarily need a telescope. This is one of the projects that Patrick is with. Could you tell us a little bit about those kinds of projects?
Yeah, so a lot of the other speakers here, they talked about, and including myself, talked about projects that can be done basically on the internet, right? Where it's basically pattern recognition. So computers can't do everything, right? And so humans are really good at seeing patterns, and so a lot of these citizen science projects that are available online, like on websites and stuff, is basically having people do pattern recognition for us. And so, like my project, for instance, is we're taking images of galaxies from all sky surveys where the contrast between the arms and interarm regions and spiral galaxies is so low that a computer can't actually pick out the individual arms, but people can see that pattern. And so we had people trace out the arms so we could just get rid of the image and just measure the arms that people showed us where they were. And that's basically our project. But everybody else's project is in a way similar to that, and that it's all kind of just pattern recognition in images that you can do online.
You don't need a telescope to do astronomy. I think Ariana right here. Oh, great.
So it must be an incredible amount of data that you get from citizen scientists. So how much do you use AI in the process of that data? Do you think that that's going to change the way the science is going forward?
I can start. Um, all of the data processing from citizen scientists that I've worked with is by a pipeline written by Unistellar that Lauren over there, thank you, supports. And every time I feel like something goes wrong, I Lauren to help me. So for that reason, the people that I work with, I don't think that AI could help. A lot of like, especially what Jackie was talking about, if you are around, is like watching the specks move across the screen over time. Those are things that it's just easier for people to do. Um, can you train AI to do whatever you want? I want to say no, but I think we all can say like not yet. Um, but I think that a lot of it and a lot of like the curiosity and wonder that drives citizen astronomers and citizen scientists and astronomy in general is people getting their hands on the data, people feeling the ownership of pulling out the telescope and doing it. So yeah, could AI make things better? Maybe, but I don't know if I would need to. Maybe this little is good.
Um, uh, with galaxy morphology, I know a lot of work in galaxy morphology is now trying to use AI to basically classify galaxies into what type of galaxy it is, and look at specific structure in galaxies as well. So it's not 100% successful, but it's getting better. And the next project that we're working on is also going to be hopefully to train an AI to pick out patterns for us as well. We'll find out if that's going to be successful or not. I'm hoping it will be. But at least in my little subfield with galaxy morphology, I think it's tending toward that, just because there's so much data available, and that I think the training is getting better and better. That eventually, computers are going to be able to pick out this morphology pretty easily. I don't know if it's going to happen in the next 5 years, but I think it'll happen eventually. Yeah.
Yeah, I'll just add on to that a little bit. I agree with what you're saying totally. I think, like everybody's been saying this whole day, the human eye is so good at pattern identification. And not that AI can't be, it just seems that right now we find different things. For Unistellar, we don't use AI at all. We don't have plans to, but I do know about projects that are. There's an active asteroid search, for example, on Zooniverse 2, where you can go and you can look for moving asteroids that are fuzzy because they're active like a comet. And for that, I think the human eye is really, really handy, and it's kind of hard to teach an AI. This moving dot is different than this moving hot pixel or something. But that's right now, and it is going to change, and it is going to get better. And I think we're going to get to the point where it's going to get really. I think maybe the next step it'll be really good at being like, this is a candidate active asteroid, and then we with our eyes confirm it, and that would help the process go faster. But the need for us to check is still there, as far as I can see.
Another question, I think, in the back over there. Yeah.
Yes. Oh, hey-o. You mentioned Japan and France in there. So I'm curious if you have any particular stories or curious instances, language barriers and cultural barriers that you found when you're collecting data and interpreting and talking to all these different citizen scientists across the world.
Yeah, sometimes. So not everybody speaks English on our Slack platform, for example. And so a lot of the time we find ourselves writing in our language, putting it through Google Translate, and then sending it to the they'll do the same thing back to us or across to each other. So sometimes things can get a little bit wonky there, but I feel like Google Translate has gotten pretty good, so it's been okay. Yeah, I don't know. I think it's been really cool to see people working together. I don't have any good stories of there being any drama or something crazy happening.
No international incidents.
No international incidents, exactly. Yeah, I don't know. I think with the technology we have, it's actually been really great, the international collaboration.
He was also supposed to tell a joke and then didn't, so I'm not letting that slide.
Okay.
How many astronomy panelists does it take to entertain the audience?
How many?
Oh, well, who knows? We're all starstruck.
That's very good. Thank you
Yep.
for that.
Yes.
I think there was a question over here. We're giving Ariana getting her steps in today.
I have a lot of them today. Where am I?
Okay. I ask this whenever I get the chance on First Fridays. What's your favorite planet? You can't say Earth. Well, that's what.
Mine is Pluto. It's Pluto. I don't care.
No.
Thank you. Thank you. Every time somebody tells me that Pluto is not a planet, I remind them that Pluto is a dwarf planet, which means it's a small planet. And just because I'm someone's little sister doesn't mean I'm not their sister. Yeah?
Well said. Well said.
Can't pick Earth. Well, yeah, it's tough. I don't know. I mean, I would say Jupiter just because it's got a lot of interesting things going on. I mean, the planet itself plus the moons are in resonant orbits, which I think is really cool. I don't know. Yeah, I'm not really into planets that much either, so I don't know. I don't know a lot of details about planets, but I mean, Jupiter is pretty cool.
Mine is Uranus for 2 reasons. One, it has a moon named Ariel. That's mine. So I like that. And two, there was a study that came out a few years ago that showed like methane gas was being ejected out of it. So like, there's all these articles about Uranus farting. I thought that was the best.
Dr. Jackson.
Oh, me. Okay, I'm gonna go with Rachel's tag and pick a world that's not strictly a planet. Saturn's moon Titan is probably the most interesting world in the solar system. Saturn has this amazing moon. It's an ice-rich moon, so that the surface is completely made of ice, but it has a very thick atmosphere. Gravity is very low, so in fact, the gravity is low, the atmosphere is thick. If you were wearing a wingsuit with wings about the width of your arms, you could actually take off on a run and launch yourself into the air by flapping your arms. NASA is going to send a mission to Titan in 2036 called Dragonfly. It's a multi-copter autonomous robot that can fly around Titan and explore this world we've never explored fully. So yeah, that's my favorite world. It's not a planet either. So. Good question.
I thought physicists were lazy. Guess not. I think you're an honorary physicist. I'm a chemist. Were there any other questions?
Is there a question? I think right in the back.
How difficult would you guys say it is to find or like get a career in astronomy compared to other sciences or other careers?
It's hard to compare just because the path I've been on is astronomy and I've been on another path. I think there are challenges for sure, and maybe this is just for academia in general. But when you, first of all, when you apply to grad school, this is a competitive process, and then you go to grad school, you get your PhD or master's, whatever you're going for. If you're going to stay in academia, there's always this fight for money. You're always applying for funding, applying for grants, hoping that your project is interesting enough to whatever panel you're writing to, and hoping that they fund it over the other hundreds of proposals that they get. That is one of the biggest challenges that I think pushes a lot of people out of academia. So I think it's really important to have, as you're starting early on, find opportunities to really connect with professors and people, and really talk to them and get to know how to write proposals and things like that. Really learn from the people that you have access to. But I think if you do that, it's really worthwhile. I really love being in astronomy. My first project.
Yeah, I don't know. I feel like it's difficult to get in. I mean, to get like a research position, like a full-time permanent research position in astronomy. Just because there are a lot of people interested in astronomy, a lot of people getting PhDs, but there aren't a lot of new positions being created. So it's, you gotta wait for somebody to retire, and then take their job, essentially, right? And so, so I feel really fortunate that I was able to get a position. I mean, I fully expected, at some point, like this is the end for me in astronomy. I'm glad I made it this far, and now I have to go do something else, like maybe programming, maybe something else, right? I was not expecting to be able to continue doing what I like doing, and so I feel really fortunate. And I work in an interesting place. I feel it's really unique that I get to work in a museum, a state-funded museum, and get to do research in astronomy for the state of North Carolina, which is, I mean, there aren't many places like that. I mean, there's American Museum of Natural History that's very similar. I mean, that has a similar program in that they have researchers working in a museum in astronomy, but there aren't many places like that. And so I feel really fortunate to have this, to be in this position. So, yeah.
I'm gonna agree. It's hard, but I feel like I'm gonna throw an optimistic spin on this, and I'm gonna tell you that astronomy is a big field, but it also means space science. So if you want to get a little creative, just kind of like Patrick was saying, like he works at a museum, which is a great place to have a job, but maybe not the first one you would think of as an undergraduate student pursuing a PhD. So I am a chemist. I am not a physicist. My PhD is in chemistry, but I still get to sit up here and talk about astronomy with you guys because I study space science. So the field expands, the better instruments get, the more data we get from space, the more we learn that any science you can do on the Earth, you can do anywhere in space. And so I think that makes astronomy a little bit more welcoming, right? I don't know. Open a door if you can't find one. It's space. It's probably out there.
I have this made me think of a question that I wanted to ask you. Obviously, we're not in this world, but if we were in a world with unlimited resources, unlimited funds, what would be your science project? What would you work on if you work on anything you wanted to work on?
I would run the Keck telescope in Hawaii because then I get to live in Hawaii.
Unlimited funds, man, that's unheard of. I mean, I've been trying to do things as cheaply as possible. I don't know. I mean, yeah, it'd be great to have just like unlimited telescope time, just to look at. I mean, if anything is possible, yeah, there are a lot of so every galaxy. I mean, galaxies tend to have like a lot of the same structure, but every galaxy really is unique. And so, I've just in my time doing this stuff, I mean, I've just seen a lot of unusual galaxies that I just want to spend a lot of time looking at and getting like good spectral data and good like deep images of like the surrounding regions, like the outer parts of these galaxies and stuff, to really understand, what these shapes are and how they're created, and run like simulations of it. So, unlimited time, I would like, unlimited telescope time and unlimited computing time would be great. But but then also I'd have to live to be like 1,000 to be able to do all this. So if we're wishing, that would be it. Yeah. Yeah.
Yeah, I mean, the first thing I think of with unlimited funds is I would give everybody a unistellar telescope in the whole wide world. And everybody would have one everywhere. We'd have no blind spots. And I would be able to travel first class to wherever I'd want to go and teach the citizen astronomers how to use the scope. And, I think that would be just awesome, like the biggest network we possibly could have. But my mind also goes to space missions. I think the reason I love the solar system so much is because there's so many questions we have about it, and we can theoretically send a spacecraft and answer those questions. The thing that stops us is funding. So I would just send every spacecraft approved and send them all.
Like pass into the spacecraft into an asteroid.
Several.
Yeah. Yeah. Other questions? Oh, yes, go ahead.
Okay, my question is, who's more fun to work with, citizen scientists or undergrads?
You say undergrads? Undergrads.
Okay, well, we have a lot of undergrads in our citizen science network. So I feel like there's like an overlap there. The undergrads I worked with directly have been like taking classes that are for non-science majors, teaching them about astronomy. And I found those extremely fun. And especially because, they're just taking this class to just get it over with and fill out the credits that they need. And so I was extra motivated to make it extra fun and silly sometimes. And so it was really fun getting them into it and making it low stakes and like that. So I really have enjoyed working with undergrads.
To be honest, I haven't really worked with undergrads. I mean, not with my citizen science stuff. The citizen scientists are great, but I do work with like a lot of high school students. So really motivated high school students contact me to ask me if they can work on stuff. And I have one student now who's brilliant. He's actually published his own first authored paper, which is amazing. But yeah, he's fantastic. I see great things in his future. And a lot of these high school students are really good and really motivated. So it's fun working with them too.
Thank you, Adrian, for this question. I a group of students back in the corner snickering. I have worked with them specifically, as well as citizen scientists astronomers, and I will say that the one benefit to working with undergrads is they are more willing to stay outside at 3 a.m. than any old Joe off the street, who is faster at responding. But everyone has their pros and cons.
Could you raise your hand again?
What would you all recommend to younger generations who want to pursue a career in science?
Keep going. Find a different way. Yeah, that's it. Keep going.
Yeah, no, I have to agree with that. It's lot of persistence. So you need a lot of. I feel like you need patience and persistence for sure. I mean, you know, liking puzzles and having problem-solving skills is good too. So basically, if you like solving puzzles and not knowing what the answer is, or even if there is an answer, I think that's part of it too. So just being curious, being patient, persevering. I think is part of it.
Yeah, I think my advice is pretty much just to shoot off of what they said. But like, take any opportunity you find and look for opportunities. If you're applying to grad schools, apply to as many as you can, as makes sense for you to do. And make sure to reach out to those professors that you want to apply to. Really create opportunities, and if an opportunity does come by, try to say yes to it. Be a yes woman. I think that's been my biggest thing. When I applied for grad school, I really didn't know much about solar system at all. I just knew I wanted to do space something because I liked that in undergrad. So I applied a little bit willy-nilly, and I felt very lucky to get accepted into a few places. And I remember the reason I said yes is because to the one I went to is because that professor opened more doors for me. It was very good about giving me opportunities, making sure I had all the opportunities possible. He invited me to visit the school. He showed me around. He told me what I was going to be doing. I really liked that, and I said yes to it. And then I learned a lot all of a sudden. But it was really scary. But yeah, I don't know. I think say yes to everything if you can.
So we're talking a little bit about career tracks and your interests and how you got. So would you tell us a little bit about maybe you were reading? Did you read science fiction when you were younger? Is there a book that really kind of stuck with you and really motivated you to pursue a career in science?
I wasn't a big like science fiction person growing up, and I'm not a big reader either. I think what got me interested was just in my classes. I found it interesting. I think I got lucky with the teachers I had. They found the science, and my math teachers, they found math really interesting, and I admired them. So I really looked up to people around me and what they were interested in. I think that's why I really found it.
Yeah, I mean, I read science fiction and I also read a lot of comic books, and I felt like the physics. I mean, I also watched a lot of Star Trek. So Star Trek was great.
We're talking about TOS or TNG?
No, TNG. Yeah, I'm of that generation. Yeah, so the Next Generation was great. They had a lot of like just interesting kind of physics storylines and stuff. And some of the some of the science fiction I read was like that too. But honestly, like some of the storylines in the comic books, I mean, they're off the charts, ridiculous. But there's always like a nugget of physics in there that they kind of run with, right? And then discovering like, oh, this is actually an idea that physicists have of possible things. So like the multiverse and things like that. Like, at first I thought, oh, this is just something they made up, but there's some root in there, right? And that actually got me more interested, and I started reading more about it.
Pull that up. So I kind of pride myself on being like the least nerdy nerd that exists. Like, I've not seen Star Wars. I've not seen Star Trek. I'm not so good at reading. Should have just let Patrick take it away.
Any other questions? Yeah, right here. All right, I'm bringing the mic.
I had a question. I guess, do you have a historic scientist or like current scientist that when you're getting into science that kind of inspired you, or like, I don't know, just
Yeah, any inspirational scientists?
I think I'm gonna go with my PhD advisor. I mean, growing up, like kind of like I said, I wasn't super into everything. I didn't know much. So the only scientist I knew was Bill Nye. I love Bill Nye. So I did idolize him for sure. But as I was learning to become a scientist in grad school, I really think I learned a lot through my advisor. I saw him, you know, basically at first I was scared of him. He was a very scary person. And I saw other people in our department scared of him, but I also saw how he thought and the way he worked through problems and stuff. And I started to really understand how his brain worked and what made him the scientist he was and the scientist that I really admired. So I really look up to him. His name is David Jewett. He's known for discovering the Kuiper Belt, so he's a really cool guy to look up to, I think.
So, to be honest, like the person that really got me interested in everything was my high school physics teacher. He was just fantastic. He knew his stuff, and my friends and I would just like ask him kind of off the wall questions, just like what if questions dealing with physics, and he would answer every single one of them, and like kind of go through the what if process with us, which was fantastic. And then he ended up also teaching the astronomy elective course that I took too. And he just kind of let us have free reign of that. Great. And then he also, he realized I was so interested in it that he gave me Stephen Hawking's Brief History of Time, and I ended up reading that too. So yeah, basically he was like the person who really got me into it for sure.
My name is Dr. Morgan Cable. Never actually met her before. But when I was in undergrad, she came to give a talk at our school, and she was the first chemist that I ever met that worked at NASA, which then meant that there were chemists that worked at NASA. So I could be a chemist and work at NASA. And she was a woman, which was also a big deal to me. She works on Enceladus and all kinds of Titan's moons. So I found her career really interesting, and I think the biggest inspiration to all of it was there was somebody, standing in the same room as me talking about all of this cool chemistry that they did, and they did it in space just like I wanted to do, and it was like, oh, there's somebody that actually does this, maybe I could too.
Great. Well, I think we'll have one more question. Any more questions in the audience?
Well, I would like to mention
Sure.
that I did invite Bill Nye to come to this conference, and his agent did not respond to me. So I think everyone needs to email him and like give him FOMO so that he'll come to the next one. Please.
So we didn't get Bill Nye, but we've had some really great, including our speakers today. We had some really great speakers come for our first Friday Astronomy. Some of you may remember that last fall we actually had Nobel Prize winner Dr. John Mather, who is a scientist at NASA and won the Nobel Prize for the Hubble mission. And so we did a series of questions just like this, where we asked them, we let the audience ask questions, one next, and one question to the next. And so I want to take the chair's prerogative and take the last question that we asked John Mather. I'm going to ask Rachel the very last question that we asked Nobel Prize winner John Mather when he visited us last year. Yeah, this is a tough one. Did you have a nice day?
I did. I had a nice day today.
Let's thank all of our panelists.
Hello again. Just wanted to thank you all. I had the chance to introduce that day of talk, speaks, exchanges, questions, and also good words by Brian. Thank you again. I just wanted to end that day before passing the mic to Rachel. First, the bad news. Unfortunately, I mean, what's good in life is that you can expect lots of things, but the weather. So it's totally overcast tonight, and we won't be able to observe the night sky, unfortunately. But Rachel will share a few things in replacement. On my side, I wanted to thanks again our sponsor. We're going to pick up 20 names to receive a free 1 year subscription to the Billion app, which is cool. We're also going to share a promo code for anyone who would like to purchase a Unistellar product by the end of next week. And from my part, thank you again to everyone. Thank you again to Brian, to all our speakers. Thanks to you. And I wish that, I think we will meet again next year in Boise, obviously. Thank you very much again. Let me pass the mic to Rachel.
Go ahead, Rachel.
Okay. So they said it's cloudy. Rachel, take the microphone. We'll see how this goes. So I quickly wanted to, maybe in 5 minutes, maybe in 6, who knows, as long as you'll bear with me, talk to you about stargazing and observing with Stellar Collective or with the Unistellar scopes. As we have talked about in the panel, I was previously a postdoc here in the physics department at Boise State Physics, and we worked with the Unistellar scopes. This one on stage is one of ours. And so I wanted to share a quick story about not only observing with the Unistellar telescopes, but one maybe a little bit closer to home, because an international network is great, but a local one is too. Okay, so mostly the goal of today, and if you were not here earlier for the talks, they will be posted on YouTube. Ariana just let me know that. So if you look up Stellar Collective on YouTube, you can look at the talks. And if you do that, or if you were here, you know that we have been talking all day about how can I use my Unistellar telescope to contribute to active science campaigns and take really cool pictures. So for one more time today, I'm going to tell you a story about how we use Unistellar telescopes to contribute to active science campaigns. If you asked me to summarize in one sentence what I do as an astronomer, I would say that I use observational astronomy to look for doomed worlds. And because you only gave me one sentence, I put some really flashy words in there. So we're going to do a little bit of a vocabulary lesson as well as go through these slides. So first, these doomed worlds come in the form of an exoplanet. If you have not heard of an exoplanet, you should probably come to First Friday more often. But an exoplanet is a planet that is orbiting anything that is not the sun. And as of 10/2, so that was yesterday, as of yesterday, there were 6,022 confirmed exoplanets, which is pretty cool. The closest exoplanet is Proxima Centauri b, which we learned from Jackie. And 75% of exoplanets are what we call transiting exoplanets. If you haven't heard of a transiting exoplanet, that is an exoplanet whose orbit crosses between Earth and its host star. And we can measure the change in brightness of the star over time to track the transit. That is one thing we do with these telescopes. And what we get out of it is a transit light curve. I promise I have a point here. Okay. So we get this nice U-shaped light curve, and we measure the exoplanet's brightness over time. And right down there at the center, the time at the minimum of the curve is called the mid-transit time. This is a very important time to me. Okay. Great. What is there to learn from a transit light curve? A lot. Things like physical parameters, the size of an exoplanet, the size of a host star, the orbital period of the exoplanet. These types of physical parameters then allow us to ask questions like, does the planet have an atmosphere? How hot is the planet? And could there be water on this planet? That's kind of a big one, especially because we have our friends from the SETI Institute here today. But instead of talking about that one, I'm going to talk to you guys about how learning about the orbital period from an exoplanet transit is really cool. So the orbital period, like I said, a vocabulary lesson. Your hint on this one is that the orbital period of the Earth is 365 days. The orbital period is the time it takes a planet to complete one full orbit around its star. So if we're watching a star and we see two transits, we know the time between those two transit midtimes are the orbital period. I'm building up to something. Okay, what makes an exoplanet doomed? This is an official NASA meme. Okay, it is a star-eat planet world. It is a decaying orbital period. The host star is pulling the planet closer. Using observational astronomy, we can track changes to the orbital period of an exoplanet. And this is something that we can do technically from our backyards here in Idaho. What does a decaying orbital period look like? Over many, many years, the orbital period decreases by seconds. Isn't that cool? You could definitely see that happen, right? But if we make it into a cartoon and we watch transits over time, we can see them getting closer and closer together. So the time in between transits is shrinking. So are we just supposed to watch all 4,000 exoplanets all the time? Ariel said if she had unlimited funds that she would give everyone a telescope. So get ready, we're watching them all. Not really. There are specific types of planets that are doomed. So this is a plot of all of the exoplanets we knew about as of June 26th, which is less than 6,000, but I promise it didn't change the demographics of this. I just forgot to update this slide. Specifically, we look at planets that are faster around their host star than Mercury. We look at planets that have a larger radius than Jupiter. And sometimes 88 days is too long. We were talking about working with undergrads. They can't stay concentrated for 88 days. So instead, we look at exoplanets that have orbital periods of about 1 day. You know, attention spans, they're short. And this is a class of planets we call ultra-hot Jupiter. Okay, we also have a really weird name of naming exoplanets. So this exoplanet in this example is called TOI 1516b. We were talking about WISE stars earlier, or you've probably heard about test planets. There's all kinds of weird ones. So I wanted to just really quickly to finish out this vocabulary list. We name an exoplanet by first starting with the mission that collected the discovery data. So for TOI 1516, that is TESS. It is called TOI because it is a test object of interest. That's a whole nother story. We're going to call it TOI. The 1516 is the number of the host star in the catalog. That's all. Most of these stars have other names, but for this specific use, this star was the 1,516th star that Tess looked at, more or less. And the B is actually the only thing that identifies it as an exoplanet. The B makes it the first exoplanet discovered around that star. Does that mean it's the closest to the star? What do you think? Raise your hands. No, it doesn't. It just means it was the first one they found. Is it more often than not the first one? Yes. Most of the time it's the closest one, but not always. Okay, so I told you I use observational astronomy to look for doomed worlds, so we're putting it all together, and we use the unistellar telescopes here at Boise State and across the state of Idaho to look for these decaying exoplanets. They're ultra-hot Jupiters. They're moving fast. They are close to their star, so they cause a big difference. And by big difference, I mean the brightness of the star changes by 1%. Okay. This past summer, we studied HAP-P37b. It is an ultra-hot Jupiter around a sun-like star. It has an orbital period of 2.8 days, and it was discovered in 2011. Those are my fast facts, and because I gave you vocabulary with it, that makes so much sense to you. And the question we wanted to ask is HAP-P37b a doomed world or something stranger? We went to all kinds of places to look for an answer for this. So we did scientific literature. We observed ourselves using the Super Pig Observing Grid, which is a citizen science project, as well as telescopes for teachers. And we most importantly, we asked for help. So we asked citizen scientists, we asked amateur astronomers to take observations of HAP-P37. to see if we could figure out what was going on with it. We collect and analyze a bunch of light curves. It's very simply a three-step process. We start by taking the observed mid-time. So we find the mid-transit time of each observation. That's again the plot above that transit light curve, the minimum. Then we calculate the mid-time. So we have one mid-time, but we actually want two. So we take what we would expect the mid-transit time to be. So for instance, the Earth has an orbital period of 365 days. So if somebody was observing us as an exoplanet, they would say our calculated mid-time is 365 days from the last one. And the next one will be in another 365 days. That's what we expect to happen. It's science, so that doesn't always happen. And that's why we keep our calculated mid-time and our observed mid-time. Step number 3 is to throw it on a plot. And yes, this plot is called an O minus C plot. It's an observed minus calculated plot. And from this, we can start to piece together out of all of the epochs. That's our last vocabulary word. Sorry, I forgot about that one. That is the number of times the planet has transited. We can look at how the observed minus calculated time changes. So this is the O minus C plot for HAPI 37 before this summer. We collected data from the scientific literature as well as data from the TESS satellite mission. And remember again, each point on this plot is its own individual transit light curve, so this does not happen quickly. But then we take out our telescopes here at Boise State University. So this is a photo from the top of the education building, if you've been able to go up there. If not, hopefully that telescope looks kind of similar to some things you've seen today. And these are transit reports from Unistellar. So we took our data, we observed with the telescope, we uploaded it to them. This is what came back to us. That made my job super easy. Okay? And so what now? We were able to add data points to this plot. So those 4 pink data points on the end are telling us those are our additions from here in Boise State. Undergrads across the room, they'll help me do this. So this is a pretty big deal, I think. And if we wanted to say that HAPI 37b was doomed, we would expect the O minus C plot to follow this kind of decaying path. Right, we would see it go down. Does it look like it's doing that? Not really. What we actually found is that instead this O minus C plot is leaning a little bit more towards a periodic or sinusoidal curve in our O minus C. That means something different, right? It's not decaying because sometimes it's shorter, but sometimes it's longer. What does that mean? That means that HAPI 37b is a stranger story than we thought, but with the help of citizen astronomers in Idaho, we are figuring it out. So that is how we can use our telescopes to do citizen science here in Idaho and around the world. But I know you're all sitting here thinking, okay, but I just wanted to see pretty pictures of space. So I thought we could do this really fun thing. Audience participation, right? So I would like everyone in the audience that has the Unistellar app downloaded on their phone to raise their hands, please. Okay, all right. If you have the Unistellar app on your phone and you have taken a picture with a Unistellar telescope that you think is really cool, keep your hand in here. Go on. Don't lie. Jacob, I bet you have one. Lauren, I know you have one. Thank you. Okay, so then look around the room, see somebody who is holding their hand up. Why don't you ask them to show off the picture they have from the Unistellar telescope, because it is cloudy tonight and I can't make it not cloudy, but I can introduce you to someone who would like to tell you about something they've seen through one of our telescopes. Okay, great. Thank you, everyone. I hope you have a great rest of your Friday.